don't have a drink, please raise your drinks. We're going to bring up the next speaker. We've got a postdoctoral scholar from UCLA. Can we please give it up for the postdocs in the house? I'd like to bring to stage Dr. Kevin Hickerson, who is working on research related to neutrinos and the weak force of the... Wait, sorry. Let's read this. The weak forces of nature. So everyone, please welcome Kevin.
Thank you, thank you. How's everybody doing? Me too. Yeah, so I'm going to talk about the invisible universe, which is something I study. Specifically neutrinos, dark matter, and there's actually dark energy in there, but I'm not even going to talk about it because it's too crazy. Okay, I want everybody to look at their glass of beer, and then look up here, and I want to hear from all the optimists in the room. Who says that this is half full? All right. Okay, you're responsible for all the cute kitten videos on YouTube, and I hate you.
The glass is twice as big as it needs to be.
Hold on. I want to hear from the pessimists in the room. Who thinks it's half empty?
I'm a pessimist, but still 100% full.
There's one pessimist?
No, I'm a pessimist.
Okay, so who is making all those dickish comments on YouTube then underneath the kitten videos? Can't just be these. All right. Okay. Well, in reality, the glass is actually 99.999999998% empty. Yeah. So the pessimists don't just win, they crush it. Sorry, optimists. No, I'm not. So what do I mean by it's mostly empty? The reality that we have found out in just this last century is that virtually everything in the universe is empty. The atoms around us, everything is almost completely empty. So, and just so you know, this very large figure here is actually just the least possible estimate. We actually don't know how empty it is. The more we probe reality, the more we find that things are smaller and smaller, but we can't actually tell how small it is. In fact, we built giant machines like the LHC in Switzerland, and that machine is basically the limit of how empty we can find space to be. And the reason I'm bringing this up and what this has to do with the invisible universe is that basically that means that if space and everything is empty, there's all sorts of things that can pass through each other, and we're not even aware of it. And that's why the universe can be mostly invisible, is because unless things are actually bumping into each other, we don't know they're there. Okay, so everybody look at your hand for a minute, or you can look at this hand for reference. There's actually trillions and trillions of particles that we know about. There's probably a lot more that we don't know about, but there's at least trillions and trillions of particles that we know about called neutrinos flowing through your hand every second. And most of these are coming from the sun. A lot of them are coming from the Big Bang. Many of them are coming from supernova, like billions of light years away. And there may be even more that we don't understand, coming from all sorts of different places. But the point is that most of these things are going on without us noticing the whole time. And so that's what I mean by that they're ghosts, is that we're essentially being crossed by particles every which way, and they just fly right through us and we don't even notice. So just to go back to that beer analogy, you may wonder, well, why does it look like it's half full or look like it's half empty, depending on your personality? The reason is because they're made of atoms, and atoms have charge, and charge interacts with light. And that's exactly what we mean when we say something is visible, is that it interacts with light. That's pretty much the definition. Our eyes see light, and so we consider that to be something that's visible. But the light is actually interacting with the charges at a distance. It's not actually physically running into it. I want to give you a brief history of the invisible universe. It actually turns out the very first thing we discovered that was invisible was a very long time ago. I don't think modern history or any history, written history, has any recording of when we first discovered this invisible thing. And I'm going to show you a picture of what this invisible thing is. Okay, so it's in this picture, and I don't want, if you know what it is, don't shout it out. Just think to yourself and feel proud. But it's in this picture. And I just want to hear like maybe applause as soon as you think you know what it is you're looking at in this picture that's invisible. All right, that's pretty good. The rest of you are going to feel dumb in a second. All right, I'm going to give you a little hint. I'm kidding about the dumb thing. Don't worry. Okay, here's my hint. Okay, who thinks they now know what's in the picture? Right, all right. Of course, it's air. Air is what's in the picture that's invisible. But the important thing I'm trying to make by this video is that the reason you can tell that air is there is because of its action on things that we can see. So we see the leaves blowing in the wind, and that's how we know that there's air. And the same, we can feel it with our hands. It makes us cold. It makes us dry, whatever. So air is a great model for what the invisible universe is like. Of course, nowadays we know from modern science and everything, air isn't actually that spectacular. It's not that different from us. We have oxygen in our bodies, and we have nitrogen in our bodies. So we now understand that there's chemicals in air that can be moved back and forth. But this was so mysterious to the ancients that they actually thought this was like a fundamental element of nature, that air was this thing that was completely, on its own, just this invisible, mysterious thing that could move back and forth. We have a very different picture of that nowadays. At the beginning of the century, this was like the model we had of the entire universe. We said, okay, so there's air and there's chemicals and there's us. So we basically put everything into a little category. We said there's protons which have charge, there's electrons that have charge, and that made up ordinary matter. And then we said everything interacts via light, and that's how we can tell if it's there. And this picture worked great for a while because it explained all chemistry in the entire universe. But there was right around the 30s, right before World War II, there was a major problem that people ran into. And that problem was this. Okay, so we had neutrons and protons inside the nucleus, and we were happy with that idea. But people started doing careful experiments, and they noticed that if you take a nucleus and it's just wandering around, sometimes it can spontaneously decay. And when it does, sometimes the particles that came off of it, they would just shoot off to one side. And this was exactly like the leaves that I showed you in the beginning. There was clearly something happening to those other particles that they would shoot off to one side, but we couldn't actually see what was causing them to shoot off to one side. There was this missing energy and momentum that was clearly there, but all we could see was the result. We couldn't see the thing itself. So this problem was solved by just an idea, and the idea was called the neutrino. And the neutrino was basically first proposed by Pauli in 1930, and Enrico Fermi later just sort of solidified the idea, and then finally Majorana did some extra mathematical work on it. Now, he didn't actually really invent that, but I bring it up for two reasons. One, he's very related to the work I do, which is trying to test whether neutrinos are Majorana neutrinos versus what's called Dirac neutrinos. I'm not going to get into what that is now, but another thing that's interesting about Majorana is that he mysteriously vanished. And what he did is he just packed up everything. He didn't leave a note or anything. He just got on a boat and he disappeared. And right. Yeah. I hadn't thought of that one. That's pretty good. My theory was that time travelers from the future came to capture him to stop him from making an atom bomb for the fascists in Italy, but he might have just fallen off the boat. We may never know. Imagine that you have this neutrino, and even though you can't see it, it's still there. And it solved the problem wonderfully. So basically, we have, you have this nucleus is coming in, and then pow, it goes off, and the neutrino is there, and it takes off that missing energy and that missing momentum. And this suddenly solved everything. It made everything make sense. But the problem is no one could see these neutrinos. So even though the atom bomb was built with this model in mind, no one knew that they were there until much later in the 50s. And then the first neutrino was detected. And the only way it was detected was because now that we understood that this was its effect that it was having on the leaves, the particles, we knew that that reverse process would also happen. So they could be detected in that same way. But it's still a very difficult thing. Okay, so then fast forward many, many decades, and this is now actually how we see the world around us. We have something called the standard model of particle physics. And here I have something called the up and down quark. And I don't want to confuse anybody, but just think of it as like the neutron and the proton. It's actually a part inside. We now found out that there's even sub-pieces of that. But they behave very much the same way the neutron and the proton work. But now we know that we have to add this neutrino in there. Well, so this is now, you can sort of think of that as like ordinary matter. And when I say ordinary, I mean it's the vast majority of what's in this room. Everything is made up of these four things, mostly. But unfortunately, nature being what it is, it's not so simple. And of course, she threw us a lot of surprises. And there's a bunch of other things. So we call these fermions. These are very similar. They obey a lot of the same rules, but they're heavier. And then we also have a bunch of more complicated interactions. In particular, there's the strong force, which is not visible originally, but it's what binds nuclei together, and that's actually where the tremendous amount of energy comes in an atomic bomb and where the energy of the sun comes from. It all comes from the strong force. Anyway, it'd be nice if this were the end of the puzzle, but this only explains the stuff that we know about today. There was one last missing piece up until a couple of years ago, and you probably heard about that. That was the Higgs boson, and that was sort of the final piece of this little mathematical puzzle that explains everything we can do in a laboratory, and it looked very promising, but it has a huge flaw. We have the standard model, it's great, but we know for sure that there's this huge collection of other stuff called dark matter. And dark matter just does not fit into this puzzle at all. And what we know about dark matter is that a lot like neutrinos, it just simply passes through us in all directions. But we cannot see it because it is, all intents and purposes, invisible to most of these interactions. But we don't know exactly how many or how. So let me tell you how we know that dark matter is there. Okay, so this is just a little simulation showing what it would look like if a piece of dark matter went across the sky. This isn't actually exactly how they do the experiment. It's just a simulation. But Einstein's theory of relativity tells us that light bends around things that have mass, and dark matter has mass. So astronomers, or astronomer friends, well, they're kind of our friend. There's some hair pulling involved. But for the most part, they came to the conclusion a long time ago, almost the same time the neutrino was proposed, that this stuff had to be there, that there was something out there. For a long time, they didn't know if it was maybe little black holes or extra planets that they couldn't see. But by the 90s, it was really obvious that it had to be something new, something that didn't fit into the standard model, because they could take pictures of the sky like that, and they could see that light was bending around something, even though there was absolutely nothing that we're used to, nothing that's made out of atoms or anything like that that we're used to. Another really strong bit of evidence for dark matter is that comes from galaxies. If you go and look out at galaxies, to an astronomer, it is so much like the leaves rustling in the wind. The galaxies rotate much faster than they should be able to. If they were able to, if they really had the mass of all the stars that you add up in a galaxy, they would actually fly apart. And astronomers do lots of careful calculations and experiments, and they know that that can't be the case. And they can actually map it out very carefully. And that's why, even though there's a little bit of distrust between us particle physicists and astronomers, we think we're on the same page here, And so now it's our collective job to figure out what this mysterious particle is. And the most amazing thing that I think is about dark matter is that we actually now know it outnumbers us significantly. There is more dark matter in the universe than there is regular matter. So that's basically it. All right. Thank you.
Questions?
So you were saying with the neutrinos early on, we couldn't detect them. Are we able to detect them now through some sort of technology, or do we just detect them because we know that they're there?
That's a good question. So the reason we can detect them now is because we found out the secret is you build your detector very carefully and you make it really, really big. So trillions of neutrinos pass through us all the time, like I said, every second. But almost none of those ever interact with your hand, which is why we don't know they're there. The trick is, if you build something big enough, eventually one of them will hit something and they will interact. And they interact via something called, in the standard model, called the weak force. And it's called the weak, that's not a euphemism. It's actually much weaker than light, and it's much weaker than the strong force. The only thing it's not weaker than is gravity, but that's a separate thing, because gravity, unfortunately, is not in the standard model yet. We have to make these detectors very carefully. We bury them underground because there's so much radioactivity and cosmic radiation. Those swamp out any signals you see. So it took a really long time before we actually were able to detect them. And the experiment I work on is, it's just like that. It's an experiment that's deep inside of a mountain. It's 1 mile under the peak of a mountain, and it's 3 miles in. And we drive it in a tunnel, and we do that because if you were to take the same detector out onto the surface of the Earth, it would just be bombarded by the daily radiation that most of us don't even know is there. Actually, that's invisible too, but that's something like the Curies discovered a long time ago. So relatively speaking, that's not even invisible.
Back here. Sorry. So you've identified it, you think you've captured it, you think you can calculate it. What can we do with it?
With which one, neutrinos or dark matter?
Dark matter.
Well, we haven't detected it yet, so I don't know what we can do with it. With neutrinos, I don't know, neutrino cell phones. Foursquare. Yeah, you.
Did you say that dark matter, what you know now, contradicts Higgs theory?
Oh, no. Doesn't oh, sorry. The question was, does dark matter contradict Higgs's theory? So the theory that Higgs and others came up with explains how mass is given to certain particles in the standard model. It doesn't disagree with models that might predict how dark matter comes about. But unfortunately, it doesn't explain dark matter either. So it's just not enough to tell us where dark matter might come from. There's actually a whole host of theories that are compatible with the current standard model that don't exactly predict where dark matter comes from. And so that's one of the things we're trying to figure out is which of this many theories explains what this is. And until we actually discover it, it's very hard to say which one's right.
Are there any theories on what makes dark matter collect to such a degree as to bend light? And then if so, also what would make it release energy?
Okay, so the question was, are there theories to explain what makes it collect and what would make it release energy? Okay, so those are both good questions. So the first one is, as far as we know, Einstein's theory of relativity says that anything that has mass or energy will cause gravity. It will gravitate. So dark matter presumably behaves just like regular matter in terms of the gravity that it has. So if you have a lump of dark matter, a planet will circle around it the same way. The big difference, though, is that regular matter clumps together because of other forces. So we have planets because the planets are sticking together independent of gravity. Like when you pick up a rock, it's stuck together by forces that are much stronger than gravity. Whereas dark matter has no other forces that strong, so it just clumps together only by gravity. So it acts much more like a gas. Then your second question was, how would it release energy? It's possible that at very high energy, dark matter annihilates itself. There might be dark matter and then anti-dark matter. So it might annihilate itself and give off regular energy, like give off light. And there's a lot of experiments. There's one on board the International Space Station, for example, and there's some others where people are looking for this annihilation. And so far, there really hasn't been any conclusive evidence that we're seeing that. Okay, I guess one more.
Anyone else?
I see. Oh yeah.
What's the size of the neutrino?
What's the size? What's the size of a neutrino? Okay, so one of the things I was trying to point out in the beginning with the beer analogy was that we don't actually know the size of particles. We can put limits on the size, but to date we've never said distinctively like this is at least fundamental particles. This is the size of a fundamental particle. So electrons, for example, we don't know how small they are. The more we probe, the smaller they seem to be. So the model that we use in the standard model assumes they're points. They have no size. We don't know if that's true because we can't probe to a point. There's also string theorists who say they're strings. So they have size, but they're one-dimensional strings. We really just don't know. That's one of the things that we're trying to figure out. Mathematically, we just say they're points. So it's possible they have zero size. Okay, I guess, all right, it looks like that's all the questions. Thank you very much.
All right, we'll be back in 15 minutes with our final presentation, so grab another drink.